You're here because you want to master displacement reactions and the thermal stability of compounds with a University of Cambridge graduate. This is actually part 2 of the Reactivity series lecture videos. If you want to watch the previous video or you want to watch the future videos in this series, be sure to check out our playlist in the link below. Hi, I'm Brendan and I'm a University of Cambridge graduate who has been teaching chemistry to many students like you over the past 9 years. I'm also the founder of the Chemistry Institution, where we have helped many students improve in a short amount of time and achieve the grades of their dreams. Be sure to check out our website in the link in the description below so that you can download a free copy of the notes for yourself and use it to run through this lecture with me today. So in general, what we have covered so far is the general reactivity series and some of the basic reactions of metals in the reactivity series with either water, steam, or dilute acids. And you can see the differences of the reactions between metals or in the reactivity series with these few reagents already. Now, what we're going to cover next is displacement reactions, and it still capitalizes on knowing the reactivity series of your metals. So your reactive metal, right, is higher in the reactivity series, okay, and in general they will displace the less reactive metals from their salts, okay, when dissolved in water. Right? So this displacement reaction is not just applicable to your metals. Okay, a recap, your displacement reactions were also found in your periodic trends when we were talking about your halogens, but it follows the same principle. In displacement, something that is more reactive will displace something that is less reactive in the same category from its salts. So the displacement of metals from a solution can be used to find the relative position of metals in the reactivity series as well. So from here, you can also judge and predict the position of metals, especially when they're unknowns in a question, in the reactivity series. Let's take a look at this table below. For your metals, right, let's say you have iron, lead, and copper, right, and you are putting them in aqueous solutions of like lead 2 nitrate, copper 2 nitrate, and silver nitrate separately. Okay, you can definitely predict what observation is going to come out based off the positions of the metals in the reactivity series. For example, iron, okay, reacting with lead 2 nitrate, we know that iron is actually more reactive than your lead 2 nitrate. Okay, so therefore your iron will win, okay, and it will displace the lead out. So your grey deposit will form. This is actually the lead coming out as a metal, okay, and a light green solution will be formed from this reaction, which is actually your iron in a salt form, which is iron 2 nitrate. Okay, so it is no surprise that these are the observations as well. Okay, so generally you want to kind of write an equation so that you know what observations will come out as well. Next, iron reacting with copper 2 nitrate. We know iron is more reactive again than copper. So iron is going to displace copper from copper 2 nitrate, right? So in other words, you're going to get this reddish brown deposit, which is the copper coming out, and a blue solution will fade. Okay, that's because your copper 2 nitrate was mostly blue, okay? But if the copper is getting displaced, then the blueness from the copper salt is going to fade away, alright? Then next, your iron reacting with silver nitrate. Your iron is more reactive again than silver, okay? So iron will win, and therefore you'll get this silvery deposit, which is actually just silver that's coming out, okay, as a metal that got displaced out, and a light green solution will form. Sorry, there's a typo over here. Alright, and this light green solution is again just your FeNO3 2 that is formed as well. Okay, so you can see from here how to predict and write the observations from reactions like this. You can also predict, okay, and see from the observations itself that iron here is definitely more reactive than your lead and your copper and your silver. Okay, now let's take a look at another example. Let's say you have lead. Okay, obviously when you try to react it with lead 2 nitrate, no reaction is going to occur because it's the same. Okay, they are the same metal. Lead reacting with copper 2 nitrate, lead is more reactive than your copper, so your lead's going to win. It's going to displace the copper out again, okay, and therefore the blue solution will fade again because your copper is coming out of its salt as well. We can look at lead reacting with silver nitrate next. Same thing, lead is more reactive than your silver, right? So your lead, okay, it's going to displace the silver out again. So the silvery deposit is the silver, okay? And lastly, your copper. Okay, your copper is very unreactive. Okay, so your copper cannot react with lead 2 nitrate because copper is not more reactive than your lead. Okay, copper with copper 2 nitrate is the same metal, so there's again no visible change. And lastly, copper compared with silver nitrate, copper is more reactive than silver. So again, you're gonna get this silvery deposit because copper is now displacing silver out of the salt. So silver is gonna come out, okay, and you're gonna get a blue solution form this time. Why? Okay, because your copper, okay, can react with your silver nitrate. Okay, and this will actually give you the silver that comes out plus your copper 2 nitrate. And we know that copper 2 nitrate is actually this blue solution that forms. This is also an important recap, right? Very often you will be asked to write ionic equations for your displacement reactions. So let's take a look at an example. In this reaction that I just wrote out as well, where copper reacts with silver nitrate, right? And silver is getting displaced out. Okay, this is the full equation. However, when we're writing the displacement reaction, usually for displacement reaction, you only need to care about that category of metals that are actually getting displaced out, or where the displacement is happening. So for example, your copper, right, is the metal that's doing the displacement, and your silver is getting displaced out. Okay, silver is the silver plus ion. Okay, the nitrate is just a spectator ion, you don't need to write this down. Okay, and therefore, this will give you copper 2 plus ion, right, plus your silver solid. And of course, let's just write the state symbols because in ionic equations, we have to write our state symbols. Next up, we can talk about the thermal stability of compounds. Now, from the reactivity series, right, remember, the more reactive the metal, okay, the more stable the compound. And therefore, it is more difficult to decompose the compound. Okay, so a few couple of points that link together, okay, but you must understand this logic. I say again, the more reactive a metal, the more stable the compound, and therefore it is more difficult to decompose the compound. So sodium and metals that are above sodium in the reactivity series, these are generally very, very reactive metals. So they will form very stable carbonates, and these carbonates actually do not get decomposed by heat. So no matter how hot you make the carbonates, right, 700 degrees, 800 degrees, it's not going to break down. It might melt, but it will not break down. Carbonates also containing metals below sodium in the reactivity series can be decomposed, okay, by heat into its metal oxide and carbon dioxide. So you must know these two products. Okay, in some cases, your metal oxide can even further decompose to form the metal and oxygen gas if the metal is super low in the reactivity series. So in general, your metal carbonates, okay, can decompose thermally, okay, to metal oxide and carbon dioxide. So for example, your calcium carbonate, okay, can thermally decompose to give calcium oxide and carbon dioxide. This is actually very usually tested with regards to the reactivity series chapter. So please understand this concept. If you take a look at this table below, right, if we go from high to low, where the highest doesn't really decompose easily from heat, as you go all the way down, it decomposes more and more easily, okay? And this is because as you go down, the reactivities of the metal will actually decrease down the series, okay? So your potassium carbonate, your sodium carbonate, these do not really change if you put in heat, okay? They do not thermally decompose as mentioned just now. Versus your calcium carbonate, your magnesium carbonate, your zinc carbonate, iron 2 carbonate, lead 2 carbonate, copper 2 carbonate. These carbonates in general will all decompose on heating, okay, and to produce your carbon dioxide and the metal oxide, for example, for zinc over here. And your silver carbonate, on the other hand, is so unreactive, okay, that this silver carbonate, right, will decompose to the metal oxide first and carbon dioxide. So that's why carbon dioxide is here, but your metal oxide will further decompose and actually give the silver and oxygen. Alright, so this is only possible because silver is very, very unreactive. So this is a special case for silver, and you actually have to memorize this whole thing. That's all for today's video. If you really learned something and you like this video, be sure to click on that like and that subscribe button so you don't miss out on free content like this. If you want to join my community of students at the Cambridge Institution, be sure to check out our link in the description below so that you can sign up for a free trial class today. Here you can learn the exact systems that we use at the Cambridge Institution to help our students improve in a short span of time and also achieve their grades of their dreams in the end.